In this video, we are going to discuss or talk about the object-image relationship. Specifically, we are going to derive the lens maker's formula. But before we do so, let's have a quick review on ray tracing method or ray diagram and identifying the location of the image as well as the characteristics of the image. So in ray tracing, if you can remember from your general physics class, we actually need two rays to be able to identify the location of your image, but we have three basic rays we can choose from. So the first ray is your central ray. You have your parallel ray and your focal ray. So let's try to draw these rays on these optical elements here. The concave mirror is a spherical mirror which looks like a cave you can crawl into. Okay. And the reflective surface is here on the left side. The center of the spherical mirror, here we denote as the C for the center, and midway is the focal point for your concave mirror. Convex mirror is a mirror which bulges towards the observer, so this is the convex mirror, and the center of curvature for this is on the other side of the mirror. And then you also have F here, C and F. For converging lens, a converging lens is a lens which converges parallel light rays into a focal point. So let's say this is your focal point, and this is center. Don't need to write the center there. Okay, and then you can write it as well. And then diverging lens. You have here diverging lens. So from its name, we know that a diverging lens diverges parallel rays, right? For central ray, say for example, we have here a mirror. We start from the tip of your ray and then it goes towards your optical axis. It will be reflected back. Following the law of reflection, of course. And then this reflection would seem to come from this point. This angle here and this angle are the same. For the convex mirror, the path of light will be the same. Rolls to the center, and then it will be reflected back as if the light comes from this direction. Now for lenses, central rays are very easy to do because your rays here are not refracted at all. So it just passes through the center. There you go. It's not changed at all. Okay. So we're done with the central ray review. How about the parallel ray? When we say parallel ray, it's actually parallel to the optical axis. So this is our optical axis here. So a parallel ray, starting from the tip of your object, okay, you have that parallel ray. Let's just draw all parallel lines first. Okay. So for parallel rays, it will be, for a concave mirror, it will be reflected passing through your focal point. This is your focal point here, and it will pass through that. And then it would come, it would as if diri siya gikan. Okay? And for the convex mirror, now a convex mirror, the focal point is located on the other side of the mirror. So what we're going to do is, it's as if it's from that focal point. Okay? So it'll be reflected like this. The real rays here will not hit the focal point, just like in similar way as we have the concave mirror, but the real ray here would seem to come from this direction. Okay. And so for converging lens, it will be similar to the concave mirror. It will pass through the focal point. Okay. And then it would seem to come from this point. It would seem to come from this direction. For the diverging lens, it will not pass through the focal point here on the other side, but it's as if it came from the focal point from the left here, because it will be diverged. The light will be diverged, so this would seem to come from this direction. Okay. So we can already, just from two rays, we can already see an intersection. And the intersection would tell you the head of your image, which means that since you have an intersection here, the image will be, let's just choose another color. The image will be here. Okay. Again, because we have an intersection at this point. For the convex mirror, the image will be here. This is not very visible. Let's change just white maybe. Okay, this is your image here. This one, you have your image here. For converging lens, you have your image here. For diverging, you have your image here. So, as I've mentioned, two rays intersecting would already define or tell us the position of your image. But three rays and will provide a better estimate of where your image would be, because ray tracing is a graphical method. So the more rays you have, the better chances of having your answer at a point close to the actual value. So let's proceed to a focal ray. We're done with the parallel ray. We proceed to the focal ray. So focal ray would pass through the focal point. So let's start with a concave mirror. A ray that passes through the focal point. We start from the head, passing through the focal point. Yes. And then it will be reflected parallel to the optical axis. As you can see, they would intersect at the same point. And this would seem to come from this direction. So the parallel ray and focal ray, they're actually partners. If you have a parallel ray coming in, it will be reflected like a focal ray. And if you have a focal ray coming in, it will be reflected like a parallel ray. For mirrors. Okay, now we proceed to convex mirrors. For a convex mirror, we cannot really hit the focal point because it's on the other side. But what we do is just try to hit. But we know we cannot really hit that. try to hit the focal point. But because of this mirror here, what will happen is that it will be reflected parallel. Oh, this should be a straight line. It will be reflected parallel as if it comes from this position. So again, you have the same intersection point. Okay, we proceed. For the converging lens, a focal ray would pass through this focal point here. This is your okay. After passing through the focal point, it will be refracted parallel. Um, doesn't look so parallel because again, this is not drawn to scale, but that should be parallel to the x-axis. It would seem to come from this direction. And for the diverging lens, you just try to hit the focal point, and then again, you'll not be able to do that. It will come out parallel as if coming from this direction. So the intersection again will tell you the head of the image. These rays here, this one's the broken dashed lines or the broken lines are what we call virtual rays. They're not the real rays, real reflected or real refracted. So these are your real rays here. Now, if the image is formed by the intersection of the real rays, you will have a real object. Sorry, real image, I mean. For example, this one, the intersection here is formed by the real outgoing light rays. So what you are able to form in this example is a real image, real and inverted. And it's actually of the same size, real, inverted, and of the same size. Here for convex mirror, the virtual rays form the intersection. And so for this case, this image is a virtual image. Size is diminished and it is upright. This one is also, this one is a real image. This one is a real image because the intersection is formed by these real rays. And for the diverging lens, these are virtual. These are virtual rays intersecting, so you have virtual image. Another way of describing a real object is also something that you can project onto a screen. So that is a real object. Otherwise, if you cannot do that, then that is a virtual image. Okay, so for exploration, I'd like you to complete this table here. This one. Complete this table for a concave mirror. You have this column object distance slightly beyond C, at C. At C is what we already did. Between C and F, or between the center of curvature and the focal point, and between the focal point and O, the origin or the optical center. So you will draw here a ray diagram. Now in this figure, the first portion you only have 2 rays, but for the other portions here, I'd like you to do the 3 rays. Central ray, parallel ray, and focal ray, and identify the image characteristics. Is it real or virtual? Is it inverted or upright? Is it magnified or diminished? So I'll just fill in this table here for a concave mirror and also for a converging lens. Now, what if we have 2 lenses? When we have 2 lenses or even multiple lenses, Say for example, I have here a converging lens, and then I have here a diverging lens. And say I have an object here. So let me define this as lens 1 and this as lens 2. And let me call this as object 1. Object 1. Oh, wait. Why is the object up there? Okay, I will not really draw the diagrams here, but I will tell you how we're going to do it, and we will do that next Thursday. So first, let's consider one element or the first optical element, and then we will work on them separately. We have object 1, we have lens 1. From this alone, just this, forgetting the lens 2, we will be able to form an image 1, right? So from here, from object 1, we can find image 1. Okay. Say for example, this is the center of curvature. Now remember that from the previous example, if this is located at C, the image 1 is here. This image 1 will be the object for the second lens. So image 1 is going to be the object 2. And now you forget about lens 1. Focus on the lens 2. This time you have an object 2 here, and from that object 2 you find the final image or the image 2. So basically that is just how we do it. The image of the first lens will become the object of the second lens. And if you have 2, 3, or more lenses, you just do that series. Okay? At this point, we're done with the review on graphical method in identifying the object-image relationship. So this time we are going to derive the lens maker's equation. And so we start with a spherical refracting surface. Let us try to draw a spherical refracting surface. Let me draw it. Okay, so for example, we have this surface here, and then we have a point A here, the location of your object, and this we label as point O as the origin or the optical center. Say for example, we have an incident light. Okay, we have an incident light at this point. Now following the law of reflection, how do we do that? Following the law of reflection, say for example, say for example, the center of curvature is here. Maybe here. Say for example, the center of curvature is here. So then the line normal to the surface will be just this, just that. Okay. So again, we have an incident light ray here going that direction. So as it hits the surface, it will be refracted. We are considering a spherical refracting surface. Let the index of refraction here be n, and here n prime, and that n prime is bigger than n. N prime is bigger than n. So if they were of the same material, the ray would have gone to this or follow this path, but then it will be refracted. So when n prime is greater than n, what would happen? Would it be refracted towards the normal line or away from the normal line? So this is n is the rarer medium and n prime is a denser medium. Okay, so it is towards the normal line. So it will be refracted towards the normal line. Okay, so let's just consider it this way. Okay. And then let's label some points. So this is our optical axis here. Okay. And we have already labeled the center. And what else do we need to label? We have this A prime here for the intersection of the optical axis and our refracted ray. Image distance and object distance. This one here will be your object distance. And this one here will be your image distance. Image distance is from O to A. So L here is OA and L prime is OA prime. We always, we just measure your distances from the optical center O. Okay. What happens next? This will be your, this here will be your angle of, this will be your angle of incidence. And this will be your angle of refraction. And let's label this point as point P. We also need to better understand the whole geometry or to derive it better. We also measure this angle here and label it as U. And then here in the image space, we label that as U prime. And this height here, we'll label it as 1. Okay. Now that we have the image, let's discuss the Cartesian sign convention. We need to have a convention in order to separate or to make a different or to differentiate the one on the left and the one on the right of your optical axis. So for the sign convention, we will be following the Cartesian sign convention. Cartesian sign convention. So first one is that distances are measured from the optical center. Distances are measured from the optical center. So this means if you measure it from here, then your L will be negative, right? This will be negative, and your L prime will be positive. so that L, again for this image, L is negative and L prime is positive. So only for this image. Okay, when your image for the different refracting surface where the image is located here on the left side, then L prime there would be negative as well. Let me just delete this one here. Just look at the figure. Okay. Next, uh, below distances are measured from the optical center. Okay. So that means above here, above the optical axis, that's a positive value, and below the optical axis, that's a negative value. So this is just a result. Let me just write the write everything here. So when it's right of lens, it will be positive. So left of lens will be negative. What else? Above the axis, above the optical axis, it will be positive, and below will be negative. Okay. What else? Now the angles here for the incident angle and the refracted angle, that should be I prime there. We already have the sign convention for that, right? For these angles here, for I and I prime, we measure from the normal line. So if it's counterclockwise from the normal line, it's positive. Again, let me just do it here. Counterclockwise from the normal line, that's positive. And then clockwise will be negative. So from the this is our normal line here. It goes into this direction. So I here is positive. This I here, angle of incidence is positive. And this one here, angle of, this is our normal line and it goes to that direction. It's also positive. Yeah, it's also positive. Okay, so what else do we need to put signs into? So we also need to have sign convention for these angles here, U and U prime. Now this is a different, this angles here would follow different sign conventions. These angles would follow the sign conventions geometrically. Okay, so we know we will be following now in we would be following a paraxial approximation for this derivation, which we'll discuss in a while. Now, if you follow the geometry here, we have tangent of u. Here is equivalent to TOA, so that's y over L. And then y is positive, it's above the optical axis, and your L here is a negative. And thus, therefore, your u here is going to have a negative sign. So this here will be negative. The sign for the angle here is negative. And for the u prime, you have a positive y here, and the l prime is positive, so u prime is just positive. Now, looking at this image, we only have two negative values here, then u and l. Okay, so these are the only two negative values that we have. So from here, I think we can now proceed with some calculations. Let me copy first this image. Oh, maybe not. Let's just erase this portion here. Okay. So our first goal is to find, now our goal now is to find the relationship between L and L prime. Let's compare the angles first, between U, alpha, and I. So this U, alpha, oh, I forgot to draw the alpha. This is our angle alpha here, which is also positive, and I. So it's just as if we have a triangle like this. Hmm. Let me use a straight line. Okay. So this is our U, this is our alpha, and this is our I. Now remember that when we have a triangle, adding all the angles will just give you what? We'll just give you 180 degrees or pi, which means that from here we can write this equation U plus U plus alpha, and this one is, this angle here is just pi minus I, right? This is just pi minus I, and this is equal to pi. So this pi and pi here gets cancelled out, and we end up having I is equal to U plus alpha. Okay, so this is our first equation, which relates the angles I, U, and alpha. Now let's go to the other angle, so other triangle, I mean. We want to find the relationship between U prime and I. So for that, we will be considering this triangle here. And let me redraw that. We have this, oh, yeah, it looks something like this. This is our I prime, and this is our alpha here, and this is our U prime. Okay, so doing the same procedure as before, we just add all these angles. We have U prime plus I, U prime plus I prime, plus this angle here, that's pi minus alpha equals pi, or 180. So the pi's here are altogether cancelled, and we end up having I prime is equal to, this one goes to the other side, so alpha minus U prime. So these two equations are from these triangles taken from this figure. Now what we're going to do here is to assume paraxial approximation. Paraxial approximation. In partial approximations, the angles are assumed to be very small. Okay, angles are very small, sine theta, such that sine theta, sine of the argument, sine theta, tangent theta is just equivalent to theta. So we will be using this approximation. Now in this figure, of course, it's not easy to have the angles very small. So the y or the vertical axis here is actually expanded or stretched. So yeah, it's actually stretched just for this figure. Now along the x-axis, the points are as is, they are not changed at all. It's just that along the vertical axis, this is already stretched out diagram. Okay. Now following this paraxial approximation, sine u, what is sine u? Here we have the angle u here. Sine u is y over L, and not sine, tangent. We'll be following tangent. Tangent is u over L. Okay, tangent u is y over L. So that means u is y over L. Okay. Again, tangent theta is opposite over adjacent, so that is just y over L. Also, for u prime, what we're having is u prime. These are u prime, and we consider this right triangle here, which involves y, so that is just y over L prime. Oh, we also have alpha. We can write alpha here. Alpha is y over distance from C. So that is just the radius of curvature. So that is just y over r. Okay. Now let's recall Snell's law. Recalling Snell's law, we have n sine I is equal to n prime sine I prime. But from our paraxial approximation, we have n sine I is just I. So ni is equal to n prime I prime. Okay, again, ni is equal to ni I prime. After which we use this equations here. So this would give us what? N. I is u plus alpha. And then n prime. I prime is alpha minus u prime. Okay. Next is we substitute or use these equations we have above. Equation 1, equation 2, so we have already used this one. And let's say this is equation 3, equation 4, and equation 5. So we substitute equations 3, 4, and 5 to this one. What we're getting is u over L, so y over L plus y over R is equal to n prime y over R minus y over L prime. Now all the terms here contains y, so we can cancel it out. And eventually we'll end up having n, what is this? N over L n over L plus n over R equals n prime over r, n prime over r minus n prime over l. Okay. And then rearranging, we have, let's just use another color for that. We have n prime over l prime minus n over l, this one, placed to the other side. And then n prime minus n over r. Okay, so this is the equation for a spherical refracting surface. Now, when we consider a lens, you have there two spherical surfaces, and so in the book, this is fondly called the lens equation. It's inside a quotation marks because there's no such thing as lens. But yeah, this formally we can call it as the spherical refracting surface equation. Or again, in the book, this is just called the line equation. For a thin lens, let's see. Let's consider a meniscus thin lens. So if we have an object here, or if we have an incident ray here, it will be incident on one surface S1, and then proceed to the second surface. So we have here surface 1 and surface 2. So basically, we just treat or consider the behavior of the two surfaces separately. Consider the behavior of the two surfaces separately. Okay. Now, let's consider for surface 1. For surface 1, what we have is just your spherical refracting surface, right? Actually, for both, we have spherical refracting surfaces. Let us just write here the equation that we got earlier, n prime over l prime minus n over l is equal to n prime minus n over r. So let's consider a case for a thin lens which is placed in or immersed in air. So this here is just air here and also air here. And then we have here an index of refraction n inside, or the lens has an index of refraction n. So for S1, we will just have the equation n prime over l prime, so that will be the region here. So let the image from the surface 1 be L1 prime Okay, so let's redo that. My mic was turned off again. So for the surface one, we have the air here on the left side, and then second medium has an index of refraction in. So comparing that to our result from the previous slide, this one is for the second medium, this one is for the first medium. And so we have n over L prime 1, because this here is image for the surface one, let's just relabel it as 1, following also the form in the book. And then minus for the second medium, oh, that's interchange. This one is for the second medium, and here, so that's n over L prime. And this one is for the first medium. And index of refraction for our first medium here is 1 for air, and then we just have L here. And then n prime again is just n, and 1 for n here, and then over R1. R1 is the radius of curvature for surface 1. So this here is our equation 1. Now let's proceed with surface 2. So for surface 2, after light after passing through S1, we will have here index of refraction for the first medium, and then second medium will be air. So using again the result that we have from the previous slide, this is for the second medium, and this for the first medium. And this time the second medium is air. So that will be 1 over L prime. We don't put 2 anymore. It's already the final image anyway. So L prime. And then minus 1. For the first medium, it's N over L prime 1. Okay. The object here is the image from the previous surface. So left hand side of the equation, we'll have it like this, and then right hand of the equation, it will be 1 for n prime, 1 minus n. Second medium minus first medium, air minus n, over the radius of curvature for the second surface. So we have now these two equations. What we're going to do then is just add these two equations, because when we add these equations, this term cancels out, right? So we end up having 1 over L prime. Then we have here from above minus 1 over L is equal to n minus 1, and then we can just negate the side here. So we can equate that to n minus 1 over R2. That way, we can rewrite the right-hand side equation of the sum as 1 over R1 minus 1 over R2. Okay. And this is the lens maker's equation. And we just, we define another variable f, which is equal to this reciprocal of the right-hand side equation, 1 over R1 minus 1 over R2. So this is what we call, again, the lens maker's equation. Yay, we have already derived the lens maker's equation. And we can, write it as this, where f there, f prime, okay, where f prime there is the focal length of the lens. Where f prime is the focal length of the lens, and so the lens maker's equation can be written as 1 over L prime minus 1 over L is equal to 1 over F prime. This is commonly known as the lens equation. Now, in your general physics class, I think the equation that you're more familiar with is this one. 1 over S plus 1 over S prime is equal to 1 over F, or 1 over F prime. So as you can see, there's a difference in sign here. The one that we have following the book of Matt Young is negative here, following the Cartesian sign convention. And this one is positive because it's following another sign convention. So we will discuss also the sign convention of this equation in another video, the video after this. So that's it then. See you in the next video.